This navigation lock works because gravity balances fluid levels naturally. The clever bit here is routing water around closed gates using internal wall culverts. When a heavy river barge enters the lower chamber, massive steel mitre doors swing shut to seal the concrete lockbox completely. Opening upper gates directly to flood the lock chamber seems like the simplest mechanical solution for raising a ship. Instead, submerged hydraulic valves quietly flood the chamber using pure hydrostatic pressure without requiring active mechanical pumping systems. If lock operators simply opened the upper gates or poured water directly over the top wall, catastrophic surface waves would instantly strike the moored vessel with immense force. Direct surface flooding creates violent turbulence within the narrow concrete chamber, causing heavy synthetic mooring lines to snap violently and threatening the structural integrity of vessel hulls. A sudden rush of surface water generates unmanageable longitudinal currents, violently pushing heavy commercial freight barges back and forth against the rough concrete chamber walls. The initial naive assumption that water can be poured directly into the lock chamber fails entirely because uncontrolled fluid kinetic energy destroys vessel stability and endangers crew safety. Engineers resolve this destructive surface surge by bypassing the main gates completely and constructing massive internal conduits buried deep inside the thick concrete lock walls. By opening controlled culverts, incoming water enters the lock chamber from beneath the vessel hull rather than cascading dramatically over the top perimeter wall structure. This deeply submerged entry path dampens initial fluid momentum, preventing large destructive surface waves from forming and preserving flat, stable water surfaces around the ascending vessel. As water rises quietly from underneath, the heavy ship floats upwards smoothly, eliminating the need for massive mechanical cables, external winches, or expensive vertical lifting cranes. The bigger problem was that simply routing high-pressure river water through wall culverts still concentrated massive kinetic energy at localized discharge points along the floor. High-velocity fluid jets blasting out of isolated culvert openings create intense localized boiling turbulence, generating dangerous tension spikes on mooring lines and shifting heavy cargo unexpectedly. Without precise hydraulic flow distribution across the entire floor, uneven water rise causes floating vessels to tilt dangerously, risking severe structural stress or wall impact. Do not suggest approaching gates, culvert outlets, restricted walls, or turbulent discharge zones. Lock currents can change suddenly, and operation belongs solely to trained lock personnel. Solving this violent hydraulic jet problem required designing an intricate internal manifold system that completely dissipates energy before water reaches the resting vessel hull.
To achieve gentle water distribution, civil engineers designed long, longitudinal culverts running inside both concrete lock walls across the full length of the chamber. Water enters the internal system through large submerged intake ports located far upstream in the upper river pool, well above the lock chamber floor level. Heavy motorized valves inside the culverts open at controlled rates, regulating fluid velocity and preventing destructive hydraulic shock waves from hammering the internal concrete tunnels. Pressurized water flows down the subterranean longitudinal wall culverts, traveling parallel to the vessel resting inside the dry concrete chamber below. Along the base of the chamber walls, dozens of smaller lateral ports branch off from the main culvert to form a distributed floor manifold array. By splitting one high-volume water stream into dozens of smaller discharge streams, the total kinetic energy is divided evenly along the entire chamber length. Specially shaped concrete floor baffles are installed directly in front of each lateral port outlet to strike the incoming high-velocity water jets head-on. These stationary baffles force opposing water streams to collide head-on, converting hazardous directional velocity into harmless microturbulence near the chamber floor. Because water enters evenly across hundreds of square meters of floor space, the vessel experiences virtually zero horizontal displacement during the entire fill cycle. Mooring lines remain slack under light tension, while pure hydrostatic lift steadily elevates thousands of metric tons of vessel and cargo weight without vibration. When the water level inside the chamber reaches exact parity with the upper river pool, hydrostatic pressure across the upper mitre gates equalizes completely. With hydrostatic forces balanced on both sides, compact hydraulic actuators open the massive upper mitre gates effortlessly, without fighting water resistance. The vessel starts its main engines and glides smoothly out of the chamber, transitioning seamlessly onto the elevated upper reach of the river navigation canal. When a vessel travels downstream, the exact reverse hydraulic process empties the lock chamber using natural gravity without requiring electric pumps. Upper culvert valves seal shut, while downstream emptying valves open, opening a clear drainage path between the lock chamber and the lower river pool.
Water drains out through floor manifold ports, entering longitudinal emptying culverts embedded deep inside the lower concrete masonry walls. The discharging water passes into a broad outlet basin equipped with energy-dissipating concrete blocks to protect the downstream riverbed from severe erosion. As water drains predictably from the bottom floor openings, the ship settles gently downward until its draft aligns with the lower river elevation.
Once internal and external water levels match, downstream mitre gates swing open smoothly, allowing the ship to pass safely into the lower river reach. This clever reliance on fundamental hydrostatics allows operators to transfer massive vessels across steep river drops using zero external pumping energy. By transforming high-pressure hydraulic streams into diffused floor inflows, engineering overcomes the physical limits of moving heavy commercial ships vertical distances safely. Submerged manifolds and energy-dissipating baffles convert violent kinetic energy into smooth, reliable buoyancy, protecting both infrastructure and vessel crews from harm. The elegant manipulation of gravity and fluid pressure renders complex mechanical lifts unnecessary, providing a permanent solution for river navigation worldwide. Understanding how internal culverts balance massive hydrostatic forces reveals the masterclass of civil engineering hidden beneath every river lock system. Through precise internal water routing and passive energy dissipation, navigation locks continuously enable global river trade across natural aquatic barriers.